For decades, planetary science felt like a solved puzzle. We had the rules. We knew the recipe. You take a star, surround it with a spinning disk of gas and dust, and over millions of years, gravity does its slow, patient work, clumping material together until planets emerge. We knew where they could form, and just as importantly, where they absolutely could not. Too close to a star, and any atmosphere gets blasted away into the cosmic void. Too far out, and things just freeze, solid. But then, a machine designed to look at the dawn of time decided to become a planet hunter. The James Webb Space Telescope was never built for this. Its primary mission was to capture the first light of the universe, to peek at galaxies that flickered into existence, billions of years before our sun was even a thought. Nobody sent it up there to break the rules of planetary science. But that is exactly what it did, and what it found has left astronomers staring at their data in disbelief, wondering if they need to throw out the textbooks and start over. The telescope became the most powerful exoplanet instrument ever built almost by accident. It turns out that when you design a machine sensitive enough to see the faintest glow from the edge of time, it is also sensitive enough to catch the chemical fingerprints of distant worlds. And those fingerprints are screaming something we never expected to hear. So here is the first bombshell. Webb has found planets in places where they simply should not exist. These are worlds orbiting stars so violent, so unstable, that any planet forming there should have been torn apart or boiled away into nothing. Yet there they are, stubborn and real, mocking our models. We thought we understood the habitable zone, that Goldilocks region where conditions are just right for life. Webb is showing us that the universe has a much broader imagination than we do. The second bombshell is just as disturbing. Webb looked at the atmospheres of these impossible planets, and what it saw defied every known law of chemistry. We have a clear understanding of how gases behave at extreme temperatures and pressures. We have tested these reactions in labs for 100 years. But these exoplanets are showing us chemical signatures that we cannot reproduce. Molecules that should have been destroyed by stellar radiation are thriving. Ratios of elements that should be impossible are lining up in perfect harmony. It is as if the universe is using a different periodic table than the one we learned in school. And then, there is the third bombshell, the one that makes even the most cautious scientists nervous. Webb detected chemical signals that tick some very specific boxes. Not proof of life, not yet, but signals that match what we would expect if something biological were at work. It could be some exotic geological process we have not seen before. But the signal is there. It is real, and it is coming from multiple worlds. Every time we think we understand how the universe builds worlds, Webb shows us how wrong we were. This documentary will show you exactly how wrong. We will walk through the evidence piece by piece. No speculation, no hype, just the raw data that is forcing us to rewrite everything. The question you need to ask yourself is simple. If our rules were wrong about where planets can exist, what else were we wrong about? For decades, the story of how planets are born was one of the neatest, most satisfying narratives in all of astronomy. It was a slow, methodical, almost patient process. We called it the core accretion model, and it made perfect sense. You start with a young star, surrounded by a swirling disk of gas and dust. Inside that disk, microscopic grains of rock and ice collide. They stick together, bit by bit, growing into pebbles, then boulders. Over the course of 10 to 100 million years, these boulders slowly clump into planetesimals, those rugged, city-sized building blocks of worlds. From there, gravity takes over. These planetesimals slam into each other in violent, chaotic mergers, forming protanoplanets. And then, after hundreds of millions of years of this cosmic bumper cars, you finally get a proper planet. A rocky world like Earth takes somewhere between 100 and 500 million years to build. A gas giant, a behemoth like Jupiter, requires a full billion years just to form its solid core, and then another few 100 million years to pull in its massive, crushing atmosphere. The timeline was strict, the recipe was fixed, and the universe, we believed, followed the rules. Now, let's bring in the real estate. We all know the Goldilocks zone. That narrow, precious band around a star where it's not too hot and not too cold, where liquid water can exist on a planet's surface. Earth sits right in the middle of this zone for our Sun, and for the longest time, this defined our entire search for life. If a planet wasn't in its star's habitable zone, we assumed it was a dead end. Too close and everything boils. Too far and everything freezes. Simple, right? This created a kind of cosmic hunting ground. We only looked for planets in that sweet spot because we assumed that was the only place where anything interesting could happen. It was logical, it was scientific, and it was also, as we're about to see, profoundly limiting. Then we have the age of the star. This was another ironclad rule. Young stars, just a few million years old, still have their protoplanetary disks. You can see them glowing in infrared, these churning cradles of future worlds. Old stars like our Sun at 5 billion years have settled systems. Their planets are formed, their orbits are stable, and the chaos is over. We assumed that if you looked at a star that was too young, you wouldn't find fully formed planets. And if you looked at a star that was too old, you wouldn't find any leftover material to make new ones. It was a clean, binary system. But again, that was based on our local experience, our single, biased data point. The Kepler mission changed our numbers, but not our assumptions. Between 2009 and 2018, Kepler confirmed over 5,000 exoplanets. 5,000 worlds. That sounds like a lot, and it is. But here's the dirty secret nobody talks about. Kepler's data is deeply, fundamentally skewed. It detected planets by watching for transits, those tiny dips in a star's brightness when a planet passes in front of it. And this method has a massive bias toward big planets, Jupiter-sized giants, and Neptune-sized worlds. It also has a huge bias toward planets with short orbital periods, meaning planets that are very close to their star. Why? Because a planet that orbits every 3 days gives you a transit signal way more often than a planet that takes 365 days. So our entire catalogue of exoplanets was, for years, a list of exactly the things we expected least. Giant planets screaming around their stars at blistering speeds. We called these gas giants hot Jupiters, and even before Webb launched, they were already a red flag. According to our models, gas giants shouldn't form that close to their star. The heat and radiation should bake away their atmosphere. But there they were. Thousands of them. We hand-waved it away, saying they must have migrated inward slowly. But the truth is, they were already breaking the rules. Then we come to the atmosphere problem. You see, a planet is a fragile thing, especially a small, rocky planet sitting close to its host star. That star is blasting out X-ray and ultraviolet radiation, what astronomers call XUV. Over millions of years, that radiation strips away the planet's atmosphere, molecule by molecule. Mars is a perfect example. It lost its thick atmosphere billions of years ago because it was too small and too exposed. So, our theory was clear. Any planet smaller than Earth that orbits closer than the habitable zone should be a barren, airless rock. No atmosphere, no chance for life. Same thing for those hot Jupiters. They should be losing their hydrogen and helium, like a leaky balloon. But they weren't. They were holding on, and we still didn't understand why. And then there are binary star systems. You know, Tatooine from Star Wars, 2 suns in the sky. We assume that kind of environment was absolutely hostile to planet formation. The gravitational chaos of 2 stars tugging on a disk of dust should, according to simulations, eject any forming planet within a few million years. It should shred the disk. It should tear apart any fragile protoplanet. The math was crystal clear. Binary systems were sterile, dead zones. Nobody even bothered looking for planets there. Why waste telescope time on something that cannot exist? We also had a clever theory about star chemistry. Based on the ratio of carbon to oxygen in a star, we thought we could predict what its planets would be made of. High carbon ratio? You get diamond planets, worlds made of graphite and carbides. High oxygen ratio? You get silicate planets, rocky worlds like Earth. This became a whole field of exoplanet geology, star chefs cooking specific planetary recipes. It was elegant, it was logical, and it was based on almost no actual data. Now, here's the kicker. What was the James Webb Space Telescope actually built to do? I want you to really understand this. The primary mission, the thing that Webb was designed for from day one, was to observe the first stars and galaxies, those ancient red-shifted objects that formed just a few 100 million years after the Big Bang. That's why it has that massive gold-coated mirror. That's why it sits at the L2 Lagrange point, 1,000,000 miles away from Earth. That's why it operates in the infrared. It was built to see the dawn of the universe. The planet atmosphere stuff? That was a bonus. Application number 2, a happy afterthought. Scientists knew it could do it, but it was never the main reason the project was funded. Webb was a time machine, not a planet hunter. That was Hubble's job, Kepler's job, not Webb's. But then the data started coming in, and, I mean literally in the very first year, the very first observations. And every single rule we just talked about, every single expectation, every foundational assumption about where planets should and should not exist, every one of them was broken. Not bent, not tweaked, broken. Young stars with fully formed planets that should have taken billions of years. Webb found them. Rocky planets in scorching orbits with intact atmospheres that should have been stripped away. Webb saw them. Gas giants in places where the carbon-oxygen ratio said they should be diamond, and they turned out to be something else entirely. Webb measured them. Planets in binary systems, stable and fully formed, orbiting two suns exactly where the math said they shouldn't be. Webb confirmed them. The habitable zone, our entire definition of it, is being redrawn because Webb found planets with water vapour in atmospheres, where the temperature should have boiled it all away. The timeline, the chemistry, the stability, the location, the atmospheric retention, every single theoretical pillar that held up our understanding of planetary formation has been cracked by 2 years of Webb data. And here is the part that keeps astronomers awake at night. This is not a problem of faulty instruments. This is not a calibration error. This is raw, physical evidence that our models are incomplete, that the universe is playing by a set of rules we haven't figured out yet. The question we have to sit with now is not whether Webb is wrong. Webb is right. The question is, what have we been getting wrong for the last 30 years? And that is the setup. That is the tension we are about to walk into. Because if our rules were wrong about where planets can exist, then we have to ask ourselves, how many worlds have we missed? How many places that we wrote off as impossible are actually teeming with possibility? The ground has shifted, and the only thing we know for sure is that we don't know anything for sure. We were just talking about how everything we thought we knew about planets might be wrong. How the old rules, the ones we carved in stone based on our own solar system, are crumbling before our eyes. And then, James Webb did something that made those crumbling pieces feel like an earthquake. It looked at a world called TRAPPIST-1b, and what it saw, well, it broke the mold completely. Imagine a system 40 light-years away, a tiny, ultra-cool red dwarf star that has almost no business hosting a family of planets. But it does. It hosts 7 of them, all roughly the size of Earth. 3 of those worlds are smack dab in the habitable zone, the perfect Goldilocks region where liquid water could exist. It was the dream target, the holy grail for exoplanet science. The first one Webb went after was TRAPPIST-1b. But here is the problem, and it is a brutal one. This planet orbits its star in just 1.5 days. Think about that. Our year is 365 days. This planet has a year that is shorter than your average work week. It is so close to its star that the radiation it receives is beyond anything we can imagine. It's bathed constantly in a torrent of high-energy particles and searing heat. For years, the scientific consensus was simple. That kind of exposure would strip any atmosphere away in a cosmic blink of an eye. The planet should be a naked, airless rock, just a burned-out cinder floating through the void. So when Webb turned its eye on TRAPPIST-1b, the first thing it did was look for an atmosphere. It used the transit method, watching the starlight filter through the planet's limb, if there was anything to filter through. The initial data rolled in. No thick atmosphere. All right, that checks out. The rock cinder model was winning. But then Webb did something more precise. It measured the thermal emission coming directly from the planet's day side, the side that is always facing the star. This is the planet's temperature measured in infrared light, and here is where things got weird. The thermal emissions showed that the surface wasn't a bare, baked rock. The temperature was there, but it wasn't matching the predictions. Something was happening on that surface that the models did not, and could not, predict. It was almost like the planet was radiating heat in a way that suggested a certain complexity, a surface that wasn't uniform. Maybe it had a thin, wispy layer of something. Maybe it had geological activity that was recycling its surface. It was the first major hint. The planet that should have been a dead world was in fact doing something. It wasn't a simple rock, it was a complicated one. And that one data point sent a shiver through the astronomy community. If a planet that close to its star can have a dynamic surface, what about the others? Then Webb moved its gaze to TRAPPIST-1c. Now, TRAPPIST-1c is a little further out, but still incredibly close. If we were going to find an atmosphere on any of these planets, this one was the best bet. The leading theory, the most logical idea, was that if any atmosphere survived, it would be a thick, crushing atmosphere of carbon dioxide, something like Venus on steroids, a runaway greenhouse world. So Webb did the most direct test imaginable. It searched for the chemical signature of carbon dioxide. If it was there, the starlight would be absorbed at specific wavelengths, leaving a fingerprint in the data. And they waited. The data came back, and it was a punch to the gut. The CO2 signature was there, but it was incredibly, shockingly weak. It was far, far weaker than any Venus-like model predicted. It was so faint that it looked like the planet had almost no atmosphere at all. So here is the dilemma, and it is a nasty one. The data gives us two choices, and both of them are deeply uncomfortable. The first choice is that these planets did have atmospheres, but they lost them. Fast. They were stripped away by the star's radiation and stellar winds in a process that we don't fully understand. That would mean our models for atmospheric escape are wrong, or at least incomplete. But the second choice is even more terrifying. It suggests that these planets never fit the model to begin with, that our entire theory of how these worlds formed is flawed. That maybe, when you're that close to a red dwarf, the raw materials for a Venus-like atmosphere just aren't available. The planets formed without them, from a different pile of space dust than we assumed. Neither answer is comfortable. One says our physics of planet destruction is wrong. The other says our physics of planet creation is wrong. And that is a very, very lonely place for a scientist to stand. As if to drive that point home, Webb turned its attention to another freak of nature. A world called 55 Cancri E. Now this is not a pale blue dot. This is a literal nightmare. 55 Cancri E is a lava world. It is a massive rocky planet that orbits its star so closely that its surface temperature is over 1700 degrees Celsius. We are talking hot enough to melt iron, to vaporize rock. The planet is a giant glowing molten ball of magma. For years we thought that such a world was just a simple static hellscape, just a giant ball of lava sitting there, boiling away. But Webb saw something that changed that picture entirely. Webb detected fluctuating thermal signals coming from the planet. The planet is outgassing. It is literally burping its interior into space. The heat from the planet's core, combined with the tidal squeezing from the nearby star, is powering monstrous volcanic eruptions. We are talking geological activity that dwarfs anything in our solar system. Here is the volcanic hypothesis, and it might be the most important idea to come out of Webb's first year. These ultra-hot worlds are not just passive victims of their star's fury. They are active, they are alive. The internal heat, fueled by radioactive decay and gravitational flexing, can pump gas back out into the void. Even if a star strips the atmosphere away, the planet can replenish it over and over again. It is a continuous cycle of destruction and creation. 55 Cancri showed us that some planets are tough, that they fight back, that the line between a dead world and a living world might be a lot blurrier than we ever thought. But then, Webb found something that made TRAPPIST-1 and the lava world look like a warm-up act. It found K2-18b, and K2-18b is the planet that started the most explosive, the most controversial, the most nerve-wracking debate in modern astronomy. This is the one that keeps astronomers up at night. K2-18b is a world that orbits its star in the habitable zone. It is about 8.6 times the mass of Earth, so it is bigger than us, but not a gas giant. We call it a sub-Neptune, a class of planet that has no analogue in our solar system. And when Webb targeted its atmosphere, it found something that should not exist. Webb detected carbon dioxide and methane simultaneously. Now, on their own, these are pretty common molecules, but the presence of both at the same time, in the ratios that Webb saw, is a screaming red flag. In an ordinary planetary atmosphere, these two gases are unstable together. They should react with each other and break down. For them to exist in such high concentrations, there has to be an active process constantly replenishing them. Something is generating these gases. On Earth, the main source of that chemical combination is life. Microbes in the ocean produce methane. Volcanoes and respiration produce CO2. But there is another, more mundane explanation, and that is just pure, high-temperature volcanic chemistry. So the debate raged. Is it geology or is it biology? But then Webb dropped the bombshell. It found a tentative signal for a molecule called dimethyl sulfide. On Earth, DMS is produced almost exclusively by living organisms. Specifically, it is produced by marine phytoplankton, the little microscopic algae in the ocean. It is the stuff that gives the sea that distinct, briny smell. It is a direct, unambiguous biosignature. Finding it on K2-18b would be staggering. It would be evidence, albeit not proof, that life exists on another world. Now, before you get too excited, we have to be careful. The signal for DMS on K2-18b is not confirmed. It is a faint potential signal buried in the noise of the data. It could be a statistical fluke. It could be an unknown chemical reaction in the planet's exotic atmosphere. We don't know. But here is the tension. It hasn't been ruled out either. The planet itself is a strange place. It is what we call a Haitian world, a theoretical category of planet that we only just invented. The theory goes that K2-18b might have no solid surface at all. Instead, it could be an ocean world, a vast, endless liquid ocean, under a thick, hydrogen-rich atmosphere. Imagine an entire planet that is just a giant, hot, pressurized ocean. Entirely new category of planet. If that's true, then any life there would not be like us. It would be extreme, adapted to a world with no land, no light, and an atmosphere of hydrogen. So here we are. The scientific community is completely divided. Half the room says it's a sign, the other half says it's a ghost. And the most chilling part is this. James Webb is going back for more data. The telescope is re-observing K2-18b. They are going to stare at it for longer, with more precise instruments. They are going to try to confirm the DMS signal, or rule it out finally. The next few months are crucial. If it is confirmed, it changes everything. If it is ruled out, we are back to scratching our heads about the CO2 and methane. Either way, the ground has shifted. We are not looking at neat little models anymore. We are looking at chaos. We are looking at a universe that is more creative, more violent and more mysterious than we ever dared to imagine. The tension surrounding K2-18b is not just a scientific debate. It is a philosophical chasm. We are standing on the edge of a cliff, and the data is the wind. The signal for dimethyl sulfide is so faint that it could be self-deception, a natural human tendency to see patterns where there are none. But the alternative is so profound that it paralyzes the imagination. This is not about little green men. This is about the fundamental nature of biochemistry. If life exists on a Haitian world, it means the universe is not just tolerant of life. It is eager to produce it. It means that given the right conditions, a warm ocean and a source of energy, matter will organize itself into complexity. It means the great filter, the theoretical barrier that prevents life from becoming intelligent and spreading across the stars, might not be the origin of life at all. The filter might be something else entirely, and that thought is deeply unsettling. Meanwhile, Webb is revealing the sheer diversity of planetary existence in a way that has outdated our textbooks. Take the case of the disappearing world. There is a planet called GJ 11132b. It is a rocky world that was once a gas giant. Its atmosphere was stripped away by its star, and all that remained was a dense metallic core. But Webb saw something that should not be there. It saw an atmosphere, a secondary atmosphere, outgassed from the planet's interior after the original one was gone. This is a planet that died and then came back to life. It is the cosmic equivalent of a phoenix. The implication is staggering. It means that planets are not fixed objects. They can evolve, change, and even regenerate. A planet that loses its atmosphere is not necessarily a dead planet forever. If it has enough internal heat, it can cook up a new one from its mantle. This process, called outgassing, is what created Earth's original atmosphere billions of years ago. We are seeing a live replay of our own planet's infancy, happening right now, 40 light-years away. Then there is the problem of the hot Jupiters. These are gas giants that orbit their stars in a matter of days, not years. For decades we thought they were simple, uniform balls of hydrogen and helium. Webb looked at one, WASP-39b, and found that its atmosphere is a chemical zoo. It has carbon dioxide, sulfur dioxide, sodium, potassium, and water vapour. But the sulfur dioxide was the surprise. That molecule requires ultraviolet light from the star to break apart other molecules and then recombine them. It is a photochemical reaction, and it was happening exactly as predicted. This confirmed a decades-old theory that we had never been able to test. It means our models for atmospheric chemistry on gas giants are basically correct. That is a relief. But then Webb found something else. It found that the atmosphere of WASP-39b is not uniform. It has clouds, but not water clouds. Clouds of silicate rock, clouds of vaporized sand. The planet is so hot, nearly 900 degrees Celsius, that rock particles are suspended in the atmosphere as a fine, glowing mist. It is raining dust on that world. Or rather, it is snowing dust, because the rock condenses at higher altitudes and falls down into the hotter depths where it vaporizes again. It is a perpetual cycle of rock rain. There is nothing like it in our entire solar system, and it is probably common. Most hot Jupiters might be hazy worlds of rock dust, not the clear, cloudless balls of gas we had imagined. But let us go back to TRAPPIST-1. The situation there has become even more dire for the habitability hypothesis. The star itself is the problem. TRAPPIST-1 is an M-dwarf, a red dwarf. These stars are notorious for their temper. They flare. They erupt. They blast their planets with high-energy radiation in sudden, unpredictable bursts. Webb observed a series of flares from TRAPPIST-1 and measured the ultraviolet output. It was worse than expected. A single flare can strip away the atmosphere of a close-in planet in a matter of hours. Now, think about the 3 planets in the habitable zone. They are not as close as TRAPPIST-1b, but they are still far closer than Earth is to the Sun. They receive a constant bombardment of X-rays and ultraviolet light. Webb's data suggests that even if these planets had thick, protective magnetic fields, the continual flaring would erode their atmospheres over timescales of a few 100 million years. That is a blink in geological time. If life ever started on those worlds, it would have been wiped out repeatedly by the stars' tantrums. Unless, and this is the crucial twist, the life evolved to survive the flares. On Earth, we have extremophiles that can survive in nuclear reactors, in boiling acid, in the vacuum of space. Could life adapt to a star that goes berserk every few days? It is not impossible, but it is a horrifying prospect. Life on a Trappist world would be a constant struggle for survival against a raging sun. And then there is the question of the magnetic field. Earth's magnetic field protects us from the solar wind. Without it, our atmosphere would have been stripped away by the sun long ago. Mars lost its magnetic field and became a desert. So, do these Trappist planets have magnetic fields? We do not know, but Webb might be able to tell us. The telescope can look for the interaction between a planet's magnetic field and the stellar wind. This interaction produces radio emissions that Webb can detect in the infrared. The first results are ambiguous, but there are hints that one of the planets, TRAPPIST-1e, has a magnetic field comparable to Earth's. That is the best hope for habitability in the system. If TRAPPIST-1e has an atmosphere and a magnetic field, it might be the one world that can hold onto its water. But the data is not conclusive yet. We are waiting. The sheer audacity of these discoveries has forced a re-evaluation of everything. The old categories, rocky, gas giant, habitable, dead, are dissolving. We are seeing a continuum of planets that blur every line we drew. There are planets that are mostly water but have no surface. There are planets that are mostly rock but have a thick hydrogen atmosphere. There are planets that orbit binary stars, planets that orbit dead stars, planets that are free-floating through the galaxy with no star at all. Webb has even found evidence of a planet forming in a disk of dust around a star, but the disk is misaligned. The planet is carving a gap in the disk that is tilted relative to the rest of the system. It is a rogue planet, growing up in a rebellious orbit. This suggests that our own solar system's neat, orderly arrangement is an exception, not the rule. Most planetary systems are chaotic. They are tilted, warped, and jumbled. And with this chaos comes a new fear. If planetary systems are so chaotic, then the conditions for life might be rare. Earth is a stable, orderly planet, with a large moon to stabilize its axis, a magnetic field, a thick atmosphere, and a star that is not a flaring monster. That combination might be vanishingly rare. But the alternative is just as terrifying. If life can exist in the hellish environments Webb is revealing, on lava worlds and Haitian oceans and sand rain gas giants, then the universe might be teeming with it. And if it is teeming, why have we not heard from it? The silence is the mystery. So, we are left with a paradox. The more we learn, the less we know. The models are breaking. The assumptions are falling. The planets are not what we thought they were. And in the data stream from Webb, we are seeing the outlines of a universe that is stranger, richer, and more terrifying than any science fiction we could have invented. The next observation of K2 to 18b is scheduled. The telescope is pointing. The photons are arriving. The answer is coming, and we are not ready for it. Either we are alone, and the universe is a dead machine of physics and chemistry, or we are not alone, and everything changes. Webb is the one holding the key, and it is turning the lock, slowly, inexorably, one photon at a time. But as Webb swings its golden eye from the distant glow of exoplanet atmospheres back toward our own cosmic backyard, something else begins to surface. Something that challenges the very foundation of how we thought planets are born. You see, for decades we had a pretty tidy picture. A star forms from a collapsing cloud of gas and dust. The leftover material swirls into a disk, and inside that disk, over millions of years, dust grains stick together, grow into pebbles, boulders, and eventually planets. It was neat, it was logical, and it was almost certainly wrong. Let me introduce you to TOI 5205b. This is a gas giant, a world roughly the size of Jupiter, but it orbits a star that is barely a quarter the size of our own Sun. The star, TOI 5205, is a red dwarf, a dim, cool, unassuming little thing. By every current model of planet formation, this star should not have a gas giant. It simply does not have enough raw material. Think about that for a second. Our Sun is massive. It contains 99.86% of all the mass in our solar system. Jupiter, the king of our planets, accounts for just over 0.1% of the Sun's mass. That is a tiny fraction, but it still required an enormous disk of gas and dust to build. Now consider TOI 5205b. The planet-to-star mass ratio here is roughly 0.3%. That is 3 times more extreme than Jupiter, compared to our Sun. It sounds like a small number, but in astrophysical terms, it is an earthquake. It is the equivalent of finding a fully grown elephant living in a studio apartment. The star simply did not have the groceries to make this meal. How do astronomers even begin to explain this? They turn to something called the pebble accretion model. The idea is elegant, really. Instead of planetesimals slowly colliding and sticking together over eons, pebble accretion suggests that small, drifting rocks, about the size of a marble or a fist, can rapidly pile up onto a growing core. These pebbles experience a gas drag that slows them down, causing them to spiral inward and get swept up by the forming planet. It is a faster, more efficient way to build a world. Theoretically, it should work even in a relatively sparse disk. But here is the catch. The conditions around TOI 5205 are so hostile, so sparse, that even pebble accretion should have failed. The disk should have been too thin, the migration timescales too short. The planet should have either starved to death or spiraled into the star and been consumed. Yet there it is, a massive world stubbornly orbiting a star that should have never given it life. And then the universe decides to rub it in. Just a year later, in 2023, astronomers announced the discovery of LHS 3154b, another gas giant. This one orbits an ultra-cool M-dwarf, a star so faint and so small it barely qualifies as a star at all. It is a dim, red ember in the dark, and it has a planet the size of Neptune. The models screamed impossible. The lead researcher on the study, Suvrath Mahadevan, put it bluntly. He said, quote, "This planet is so massive that it shouldn't exist." That is not hyperbole. That is a professional astrophysicist staring at the data and admitting the textbooks need to be rewritten. LHS 3154b was the third such planet discovered in just 2 years. 3 impossible worlds. 3 cosmic middle fingers aimed directly at our tidy formation theories. So what is going on? Are our models wrong? Or is the universe just messing with us? The answer, as Webb is showing us, might be even stranger. Because the problem is no longer just about planets forming around stars that are too small. It is about planets forming with no stars at all. Let us travel to the Orion Nebula. It is one of the most beautiful and familiar sights in the night sky, a stellar nursery sprawling across 1,300 light-years of space. We have looked at it for centuries, but we had never seen it like this. When Webb turned its infrared gaze toward the heart of the nebula, it revealed something that left astronomers shaking their heads in disbelief. Hundreds of rogue planet-like objects. Not brown dwarfs. Not failed stars. Worlds with masses comparable to Jupiter, floating freely through the nebula with absolutely no parent star. They are orphans, wanderers. Planets untethered from any sun. By itself, this was shocking enough. Rogue planets had been predicted, but never in such staggering numbers. But then Webb zoomed in closer, and the real madness began. These objects were not alone. They were in pairs. Binary pairs. 2 Jupiter-mass objects orbiting each other, locked in a gravitational dance, with no star anywhere nearby. They called them Jumbios, Jupiter-mass binary objects. Think about what this means. You have 2 planet-sized objects, each roughly the mass of Jupiter, orbiting each other in the cold, dark void. By every definition, they look like a binary star system, minus the stars. They are twins, born together, travelling together, with no parent star to call home. And this absolutely breaks every known model of planet formation. We have 3 leading theories for how they could exist, and every single one of them makes the astronomers who proposed them deeply uncomfortable. Theory number 1, ejection. Maybe these things were born in a normal solar system inside a protoplanetary disk, and then some violent gravitational interaction flung them out into the void. This happens. We have seen evidence of ejected planets before, but here is the problem. To eject a planet, you usually need a massive gravitational kick from another planet, or a passing star. That kind of event is chaotic. It should tear binary pairs apart. It should scatter them in random directions. The chance of 2 planets being ejected together, still gravitationally bound to each other, is astronomically tiny. You would need a near-perfect synchronized escape. It is possible, but it feels like winning the cosmic lottery twice. Theory number 2, direct condensation. Maybe these objects did not form in a disk at all. Maybe they condensed directly from the gas and dust of the nebula itself, the same way stars form, but they just never gathered enough mass to ignite fusion. That would make them a type of brown dwarf, a failed star. But again, there is a problem. Brown dwarfs rarely come in such perfectly matched pairs, and they certainly do not come in the numbers we are seeing. The Orion Nebula is absolutely packed with these jumbios. It would mean that the nebula is somehow fragmenting into thousands of tiny paired objects, an entirely new class of celestial body we never knew existed. Theory number 3, an unknown mechanism. This is the scientific equivalent of throwing your hands in the air. It is a confession, a plea. We do not know. Something else is happening out there. Some force, some process we have never observed is building these worlds. And if you are a scientist, this is both the most terrifying and the most exciting option, because it means the universe still has secrets, big ones, and the strangeness does not stop at the edges of the Orion Nebula. Webb has also been peering into the hearts of globular clusters. These are ancient, densely packed balls of stars, some of the oldest structures in the universe. For decades, astronomers assumed that planets could not exist in these environments. The reasoning was solid. Globular clusters are chaotic. Stars are packed so tightly together that gravitational interactions are constant and violent. Any forming planet would be torn away from its star, or have its orbit scrambled, before it could ever fully form. It was an ironclad rule. Planets are for quiet neighbourhoods, not cosmic slums. Webb shattered that rule. It found planets in globular clusters. Not just a few, not just rocky scraps. Planets, fully formed, persisting in the most crowded, hostile environments imaginable. It is like finding coral reefs thriving in a washing machine. Then there are the circumbinary planets, the Tatooines. Planets that orbit not one star, but 2. If you thought the physics of a single star system was tricky, try calculating a stable orbit around a binary star system. The gravitational forces from 2 suns pulling and tugging at the same time create regions of chaos where no planet should be able to survive long term. The math is brutal. Most orbits in a binary system are unstable. They are destined to either crash into one of the stars or be flung out into interstellar space. But Webb has found several circumbinary planets in systems where the orbital mechanics should be mathematically impossible. They are hanging in there, swinging around twin suns, stubbornly refusing to be ejected. They should not exist, they do. And finally we arrive at WASP 39b. This is a world that is actively being destroyed. It is a gas giant so incredibly hot, so close to its parent star, that its atmosphere is being blasted away into space. We have seen this before. We call them hot Jupiters. But Webb did something unprecedented. It watched the atmosphere break apart in real time. It detected photochemistry happening live, right before its virtual eyes. Ultraviolet light from the star is tearing the molecules apart, stripping the planet of its outer layers, layer by layer. WASP-39b is dying, and yet there it is, still whole, still there. The models say it should have been stripped to its core long ago. But the planet persists. It is holding on, surviving in a regime of constant, violent destruction. So what do we make of all this? Planets where there should be no material, planets with no stars, planets in the densest clusters, planets orbiting two suns, planets being torn apart but refusing to die. The thread through all of this is that our understanding of planet formation is incomplete. It is not just a few details we need to tweak. The entire framework is being challenged. We built our models based on our own solar system, a single data point, a quiet, stable, middle-aged star with a handful of planets in neat, orderly orbits. We assumed that was the template. It is not. It never was. The universe is building worlds in ways we never imagined, and Webb is showing us exactly how wrong our maps were. Every single one of these discoveries is a crack in the old paradigm, and through those cracks, a new universe is leaking in, one far stranger, far more fertile, and far less predictable than we ever dared to dream. But to truly understand the depth of this crisis, we must step back and look at the history of the idea itself. For most of human history, the question was not how planets formed, but whether they existed at all. The ancient Greeks speculated about other worlds, but their cosmology was geocentric, closed, perfect. The crystalline spheres of Aristotle had no room for rogue worlds or binary jumbios. When Copernicus moved the sun to the centre, he opened the door to a solar system that was just one of many. Giordano Bruno, burned at the stake in 1600, dared to suggest that the stars were other suns surrounded by their own planets. He was right, but he was 3 centuries too early. The tools did not exist. The evidence could not be seen. It was not until the 1990s that the first exoplanets were confirmed, and when they arrived, they were utterly alien. Hot Jupiters. Gas giants orbiting their stars in mere days, with orbits so tight they should have been impossible. The field of planet formation was thrown into chaos overnight. The models had predicted we would find systems like our own. Instead, we found monsters. But those early discoveries were made using the radial velocity method, a clever trick of measuring a star's wobble, but it could only give us mass and orbit. We could not see the planets. We could not smell their atmospheres. We were blind people in a dark room, groping for the shape of an elephant we did not know existed. Then came Kepler, the transit method. Watching stars dim as planets passed in front of them, Kepler gave us thousands of worlds. It filled the census. It told us that most stars have planets, and that small rocky worlds are common. But Kepler gave us a catalogue, not a story. It could tell us a planet was there, but it could not tell us what it was made of, or how it got there. The models remained. The contradictions remained. And then, after a 30-year wait, after a decade of delays, and a budget that nearly killed it, the James Webb Space Telescope finally launched. Webb is not a telescope. It is a time machine with a mirror the size of a tennis court, orbiting 1 million miles from Earth at a place called Lagrange Point 2. It sees the universe in infrared, the heat of creation itself. And because light takes time to travel, the farther Webb looks, the further back in time it sees. It has already peered at galaxies that formed just 300 million years after the Big Bang. But we are not here to talk about galaxies. We are here to talk about planets. And Webb has turned its infrared eye on the disks where planets are born. These disks, called protoplanetary disks, were once thought to be simple. A flat, pancake-like structure of gas and dust rotating around a young star. The dust settles. It clumps. It grows. But Webb's infrared spectrographs have revealed a nightmare of complexity. The disks are not smooth. They are riddled with gaps, rings, spirals, and shadows. They are warped by the gravity of forming planets that carve out paths as they grow. Webb can see the chemical fingerprints of water, carbon dioxide, methane, and even complex organic molecules swirling in these disks. The building blocks of life are everywhere, but the structures themselves are violent. The disks are turbulent, and in that turbulence the old models of gentle, slow accretion do not hold. The planets are not being built in a calm nursery, they are being forged in a storm. Consider the disk around HL Tauri, a young star about 450 light-years away. The Atacama Large Millimeter Array, ALMA, gave us the first jaw-dropping image of its rings and gaps. It looked like a fingerprint, a series of concentric circles carved out by unseen planets. But the shocking part was the age. HL Tauri is only about 1 million years old. By planetary standards, it is an infant. And yet, the gaps in its disk suggest that planets several times the mass of Earth have already formed. That is impossibly fast. Our own solar system took tens of millions of years to build Jupiter. But here, in a system barely old enough to have a stable orbit, planets are already carving their signatures. The models said planet formation should be slow. The evidence says it is fast. Very fast. Now apply that speed to the problem of the jumbios in Orion. If planets can form in 1 million years, then perhaps they can form in the collapsing gas of a nebula itself without a star. Perhaps the filaments of gas that weave through the Orion Nebula are dense enough to fragment directly into planet mass objects. And perhaps those fragments are born in pairs, spinning off from the same turbulent eddy, locked in a binary dance from the very first moment of their existence. It would be a new mode of formation, a third path alongside the classic core accretion and the gravitational instability of disks. It would mean that planets are not only the children of stars, but can be born directly from the interstellar medium, like seeds sprouting in the void. But even this explanation strains under the numbers. The Orion Nebula is not a gentle mist. It is a region of intense radiation from massive stars, ultraviolet photons that should strip away gas and prevent the formation of low-mass objects. The JUMBOs should have been photoevaporated, boiled away before they could condense. Yet they persist, they thrive. There is a missing piece, a mechanism we have not yet identified. And as Webb continues to survey the nebula, it is not just finding more jumbios. It is finding them in regions of the nebula that are the most hostile, the most irradiated. They should not be there, but they are. And then there is the question of their atmospheres. Webb's ability to perform spectroscopy on these objects, to split their light into a rainbow and read the chemical composition, is the next frontier. If the JUMBOs have atmospheres rich in elements that can only be formed inside a protoplanetary disk, like certain ratios of carbon and oxygen, then they must have been born around a star and ejected. But if their atmospheres match the raw composition of the nebula itself, then they are true orphans born in the void. The answer to that question will rewrite the textbooks, and we are waiting. The data is coming. Meanwhile, back in the realm of conventional planets, the contradictions continue to pile up. Consider the case of the TRAPPIST-1 system, a tiny ultra-cool red dwarf star, just a fraction of the mass of our Sun, surrounded by 7 Earth-sized planets. 3 of them orbit within the habitable zone. It is a dream system for astrobiology. But it is a nightmare for planet formation. The planets are packed so tightly together that their gravitational fields interact constantly. The system is a resonant chain, a delicate ballet where each planet tugs on its neighbours in perfect synchrony. The models say such a system should be unstable on timescales of millions of years. Yet it has survived for billions. And the planets themselves are so close to their star that the protoplanetary disk should have been too hot for ice to exist. But water is essential for building Earth-sized planets. Without ice, the pebbles needed for rapid accretion cannot form. TRAPPIST-1 should not exist. It does. Perhaps the most profound implication of all this is that we have been looking at planet formation through the wrong lens. We have treated it as a purely mechanical process: gravity, dust, gas, time. But Webb is showing us that chemistry is just as important, if not more so. The molecules in a disk determine how dust sticks together, The ionization levels, driven by radiation from the star, determine how gas moves. The presence of water ice determines where the snowline falls, the critical boundary where planets can form quickly, and Webb is finding that these snowlines are not fixed. They move. They fluctuate as the young star brightens and dims, as flares erupt, as the disk evolves. Planet formation is not a static assembly line. It is a chaotic chemical reaction happening on a planetary scale. We are only 3 years into Webb's mission. It has a decade of fuel left, possibly more, and it has already turned our understanding of the cosmos on its head. The next targets are already being selected. The disks around the youngest stars, the atmospheres of the Jumbios in Orion, the chemical fingerprints of the orphan worlds in globular clusters, and deeper into the past, the first exoplanets that ever formed, worlds that lit up in the darkness of the early universe, when the first stars and the first galaxies were just beginning to shine. Did planets form back then? The models say no. The heavy elements needed for dust, for rocks, for planets were not abundant. But Webb is finding galaxies filled with dust only a few 100 million years after the Big Bang. Something enriched them faster than we thought. And if dust was there, planets could have been there too. We are standing on the edge of a revolution. The old certainties are gone, the neat diagrams of protoplanetary disks, the tidy timelines of planetary evolution, the simple rules of what is possible and what is not. All of it is being shattered by a stream of infrared photons collected by a golden mirror 1,000,000 miles from home. The universe is not just stranger than we imagine, it is stranger than we can imagine. And we are only just beginning to open our eyes. The previous section ended with the sentence, "The rules of what is possible and what is not, all of it is being shattered by a stream of infrared photons collected by a golden mirror 1,000,000 miles from home." The universe is not just stranger than we imagine, it is stranger than we can imagine. And we are only just beginning to open our eyes. Let's talk about the ancient planet problem. Because if you think you understand how planets form, you are about to have your entire worldview turned upside down. For decades, astronomers had a pretty neat tied-up story about the early universe. It was a simple, clean narrative. The universe after the Big Bang was a hot, roiling soup of hydrogen, helium, and a sprinkle of lithium. That's it. No carbon. No oxygen, no iron, nothing that you or I are made of, nothing that makes a planet. Those heavier elements, what astronomers call metals, didn't exist yet. They had to be forged in the cores of the first generation of stars, cooked over billions of years in a stellar nuclear furnace, and then scattered across space when those stars exploded. Only then, when the cosmos was properly polluted with the ashes of countless dead suns, could rocky planets begin to form. It was a logical, step-by-step process. You need the raw materials before you can build a house, so the theory went, the early universe was a barren wasteland for world building. There simply were not enough heavy elements to glue together a planet. No silicon for the crust, no iron for the core, no carbon for the chemistry of life. For the first several billion years, the cosmos was supposed to be a desert of endless gas giants, if any planets at all. Then we found Kepler 444. This is where the problem gets real. Kepler 44 is a star system that is 11.2 billion years old. Let that number sink in for a moment. The universe itself is only about 13.8 billion years old. That means this star, this whole system, formed when the universe was a cosmic toddler, barely 2 billion years old. And what did we find circling this ancient metal poor star? Not gas giants, not frozen ice balls, 5 rocky planets, confirmed. Rocky, terrestrial worlds, orbiting a star that, by all accounts, should not have had the ingredients to make them. This is like finding a fully assembled brick skyscraper in the middle of a desert where you haven't even discovered a brick factory yet. It just should not be there. The star itself is what we call a metal poor star. It has less than a quarter of the heavy elements that our own sun has. By the standard model of planet formation, the core accretion model, you need a certain threshold of dust and heavy material to get the process started. You need things to stick together, to clump, to snowball into something the size of a planet. If there is not enough heavy stuff floating around, the particles just bounce off each other or get blown away by the solar wind. It is the planetary version of trying to build a sandcastle with 20 grains of sand. But Kepler 444 did it anyway. It built a family of rocky planets when the universe was practically brand new. So what does that mean? It means one of two things. Either our models of planet formation are fundamentally wrong, or there was an entirely new mechanical process happening in the early universe that we have never accounted for. Maybe the young universe was a more chaotic, violent place that allowed for some other kind of accretion. Maybe there were massive dust clumps created by the sheer turbulent pressure of the first stellar explosions, compressing material into lumps faster than we thought possible. Or maybe the dust grains themselves were larger and stickier in a low-metal environment. We do not know. But the data is there, the exoplanets are there, and they are forcing us to rewrite the textbooks. The James Webb Space Telescope was built to look at these ancient systems, not just to find them, but to study their atmospheres. And what it has found there is even more disturbing. Webb looked at these billion-year-old rocky worlds and performed spectroscopy on them, splitting their light into a rainbow to see what chemicals were absorbing those specific wavelengths. And the signature was unmistakable. These ancient planets have preserved atmospheres. They have held onto their gaseous envelopes for over 10 billion years. That is the part that breaks the models. A planet's atmosphere is like a leaky balloon. Over vast stretches of time, the solar wind from a star strips that gas away into space. To keep an atmosphere for 1 billion years is hard. To keep it for 5 billion years is almost miraculous. To keep it for 10 billion years, that should be impossible. Especially around an old active star that was likely much more violent in its youth. But the atmospheric signatures are there. The Webb data is clear. There is gas. There is retained chemistry. There is a world that has kept its blanket for practically the entire history of time. Now, think about what that implies for life. If these ancient rocky planets can hold on to their atmospheres, they can hold on to water, they can maintain a stable surface temperature, they can protect themselves from radiation. They had a 3 billion year head start on Earth. 3 billion years. Earth is 4.5 billion years old, and complex life only really exploded on a macroscopic scale about 500 million years ago. That means these ancient worlds had an entire extra life cycle, an entire extra window of opportunity that we simply did not know existed. Life on Earth had a relatively late start in the cosmic calendar. But these planets, they were ready for biology just a few 100 million years after the Big Bang. The universe was building potential homes for life almost as soon as it had the materials. And if life can arise in 1 billion years, and we have reason to believe it can, then life on those ancient worlds could have been thriving, evolving, and building complexity, while our own solar system was still just a collapsing cloud of dust. It is a humbling thought. We thought we were the new kids on the block, but we might be the latecomers to a party that started 10 billion years ago. But the problems do not stop with ancient atmospheres. We have to talk about TOI 561. This is a system that is 10 billion years old, and it has a planet, TOI 561b, that is a nightmare for orbital mechanics. This is an ultra-short period rocky planet. It completes a full orbit around its star in just 10.5 hours. That is less than half an Earth day. It swings around its star so fast and so close that its surface temperature likely reaches thousands of degrees. The star in question is a thick disk star, one of the oldest populations in our galaxy, and this planet should not exist. According to the physics of tidal disruption, most close-in rocky planets of this type should spiral into their parent star within 1 billion years. The gravitational interaction causes tidal forces that drain orbital energy, pulling the planet inward until it is shredded and consumed. It is the same mechanism that causes the Moon to slowly move away from Earth, except in this case, it works in reverse, pulling the planet in. For a planet to survive that orbital dance for 10 billion years is like a skydiver free-falling from the edge of space, hitting the ground at terminal velocity, and then standing up and asking for a glass of water. It just does not fit the math. Astronomers have a hypothesis to explain this, and it is a beautiful bit of theoretical gymnastics. It is called the resonance hypothesis. The idea is that some planets get locked into very specific gravitational resonances with their star, where the orbital periods and rotation rates are locked in a perfect sync that effectively cancels out the tidal decay. It is like a pendulum being pushed at exactly the right frequency to keep it swinging forever, never losing energy. The planet is essentially surfing a wave of gravity that prevents it from sinking. But here is the catch. Maintaining that perfect resonance for 10 billion years is not just hard, it is extraordinary. One wrong nudge from a passing star, one gravitational perturbation from another planet, and the whole system collapses, sending the world spiraling into destruction. The fact that TOI 561b is still there, still hanging on after all this time, is a statistical miracle. Either the system is impossibly stable, or we are missing a fundamental piece of the physics puzzle. And then we have the supernova survivors. Webb has discovered planets in systems that have experienced supernovae. Stellar explosions, the most violent events in the universe, should have vaporized any close companions. But some planets survived. They were just at the right distance, or they had enough mass to ride the shockwave without being torn apart. This feeds into a theory that is gaining traction, the second-generation planet theory. The idea that some planets are not made from pristine nebula gas and dust. They are made from the recycled debris of dead stars. Pulsar planets, rocky worlds orbiting the remains of exploded suns, have been known for decades. But Webb has found more of them, and it is finding them in places we did not expect. These are worlds literally forged from the ashes of cosmic destruction. They are not only survivors, they are direct descendants of stellar death. So let's wrap this up with the big picture. The universe has been building planets longer than we ever thought possible. And if those planets can hold on to atmospheres for billions of years, then life had a head start we never accounted for. We are not the first opportunity that the cosmos had. We might be the 10,000th. Every ancient world we find, every survivor of tidal decay, every planet that held its breath for 10 billion years, is a reminder that the story of the universe is far older, far richer, and far more robust than we ever imagined. The James Webb Space Telescope is not just finding exoplanets that should not exist. It is finding a universe that was waiting, patient and ready, long before we ever arrived. And so, with that cosmic perspective firmly in mind, we turn our gaze from the grand sweep of time to the microscopic chaos of chemistry. Because if you thought the planets themselves were breaking the rules, wait until you see what their air is made of. This is where the James Webb Space Telescope transforms from a simple picture taker into something far more profound. A forensic chemist analysing the ghostly signatures of light that have travelled for years across the void to land on its golden mirrors. You see, when a planet crosses in front of its star, it is not just blocking a little bit of light. It is revealing itself. Starlight filters through the thin skin of the planet's atmosphere, and every single molecule in that air leaves its own unique fingerprint in the light that passes through. It is like a cosmic barcode, and Webb can read it from trillions of miles away. This is infrared spectroscopy, and it is the single most powerful tool we have ever built for understanding what alien worlds are actually made of. And the very first big test of this tool was a planet called WASP-39b, a bloated hot gas giant orbiting a star about 700 light-years away. In September of 2022, The world watched as NASA announced Webb's first major exoplanet triumph. The clear, unambiguous detection of carbon dioxide in WASP-39b's atmosphere. This was the first time CO2 had ever been confirmed on a planet outside our solar system. It was a landmark moment, a celebration. But if you were paying close attention to the data, something was a little off. The ratios were wrong. The amount of carbon dioxide relative to other gases did not match a single one of the pre-existing atmospheric models. In other words, the planet was acting like it had read a different instruction manual. But that was just the appetizer. The real shocker came when Webb looked a little closer. It found sulfur dioxide in that same atmosphere. And here is the thing. No model, no computer simulation, no piece of theoretical work published before Webb launched had ever predicted sulfur dioxide would be there. Not one. You see, sulfur dioxide, or SO2, is a tricky molecule. On Earth, it is produced by volcanoes. But on a planet like WASP-39b, which is baking at thousands of degrees, it was assumed that any sulfur compounds would be torn apart instantly. But they were not. They were there, floating in the air, as if they owned the place. The explanation turned out to be photochemistry. Light from the planet's host star is so intense that it actually drives chemical reactions in the upper atmosphere, creating sulfur dioxide from simpler molecules. This is the first time we have ever seen photochemistry at work on an exoplanet. It is a process we have studied in Earth's own ozone layer. But to see it happening on a world hundreds of light years away, in conditions that are completely alien to us, well, that changed the game entirely. The surprise was that the sulfur compounds should not have survived. The models said they could not. And yet there they were. So either the models are missing a vital formation pathway, or there is some kind of replenishment mechanism constantly pumping fresh material into the sky. Either way, the textbooks are getting rewritten whether they like it or not. And this is not a one-off anomaly. This is a pattern. Water vapour, for example, has now been detected in the atmospheres of hundreds of exoplanets. It is everywhere. You would think we understand it by now. But the quantities are all wrong. They are consistently off. On some planets, the air is much drier than models predicted. On others, it is sopping wet, bursting with steam in ways that make no sense, given the planet's orbital distance and temperature. The simple theoretical relationships between a planet's size, its heat, and its water content have been thrown out the window. The universe is not following our recipes. This leads us to a concept that is driving planetary scientists absolutely up the wall: chemical disequilibrium. Put simply, if you mix certain gases in a container, they will react with each other and eventually settle into a stable state. That is equilibrium. It is boring, it is predictable. But on Earth we have something strange. Oxygen and methane exist together in our atmosphere, and those two gases really do not get along. They should react away, consuming each other almost instantly. The only reason they do not is that something is constantly making a fresh supply. On our planet, that something is life. Trees pump out oxygen. Microbes belch methane. Together, they keep the atmosphere in a state of constant imbalance, a chemical tug-of-war that screams out. Something alive is here. Now, take that idea and apply it to the exoplanets. Webb is now probing. If we find an atmosphere where gases are present that should have reacted away long ago, it is a huge red flag. It tells us that something active is driving the chemistry. It could be geology, it could be volcanism, or it could be biology. This is why the debate over phosphine on Venus got so heated a few years back. Phosphine is a nasty, smelly gas that on Earth is almost exclusively produced by industrial processes or by microbes living in oxygen-free environments. When it was tentatively detected in the clouds of Venus, the scientific community exploded. The detection was later disputed. It remains one of the most controversial claims in modern astronomy. But here is the key point. Webb can now search for phosphine in the atmospheres of exoplanets with an accuracy we could only dream of before. If we find phosphine on a temperate, rocky world where there is no known geological source, the implications are staggering. It would be the strongest hint of life we have ever found beyond Earth. But the rule breaking does not stop there. Webb has found worlds with carbon-rich atmospheres, skies loaded with soot and hydrocarbons, on planets that should, by all accounts, be dominated by oxygen. The prevailing theory of planet formation near Sun-like stars predicts that oxygen should be the dominant player. It is the third most abundant element in the universe. It should win. But reality disagrees. On some of these worlds, carbon wins. The atmosphere is soaked in it. That means the whole chemical recipe for that planet was different from the start. The building blocks were different. The star and the planet did not share the same composition, and no one can fully explain why. Then there are the clouds. Not the fluffy water clouds we see from an airplane window, silicate clouds, clouds made of vaporized rock, tiny microscopic grains of molten glass floating in the upper atmosphere of a planet called WASP 103b. This was the first time such clouds have ever been detected on an exoplanet. And they are layered, just like Earth's cloud decks. But instead of water droplets, they are droplets of liquid rock. Imagine standing on the surface of that world, if you could survive for even a fraction of a second, and looking up to see a sky made of sand and glass, swirling in the heat. It is beautiful, it is terrifying, and it was not predicted. And finally, we have the metallicity problem. This one is subtle, but it goes to the very core of how we think planets form. Astronomers use the word metal to mean any element heavier than helium. So when we talk about metallicity, we are talking about how much carbon, oxygen, iron, silicon a star or planet contains. The simple, logical assumption was that a planet's atmosphere should reflect the composition of its host star. The star is the mother, the planet is the child. They should share the same elemental bloodline. But Webb has shown that this is not true. Exoplanet atmospheres are consistently, stubbornly more metal-rich than their parent stars. Something happened during the planet's formation to concentrate the heavy stuff. Whether it was the way the planet accreted material, or how it later lost its lighter gases, or some process we have not even considered, the models are failing. The universe is not a tidy laboratory. It is a messy, chaotic, glorious riot. And that is the lesson Webb is teaching us day after day. We built these models based on one sample, our own solar system. We assumed the rules were universal. They are not. The chemistry of planets is far more diverse, far more violent, and far more creative than we ever gave it credit for. Every new spectrum Webb sends back is a demolition crew taking a wrecking ball to our comfortable assumptions. Chemistry is the language of planets, and Webb is revealing that we were barely speaking the alphabet. We must now reckon with a deeper, more unsettling implication. If the chemistry of these alien atmospheres is so wildly different from our predictions, if every spectrum is a surprise, then we have to ask ourselves a very uncomfortable question. Are we even looking for signs of life in the right way? The answer, it turns out, is probably not. Consider the holy grail of exoplanet science, the search for biosignatures. For decades, the strategy is straightforward. Find a rocky, temperate planet. Look for the simultaneous presence of oxygen and methane, the two gases that on Earth are locked in a perpetual chemical war, kept in imbalance only by the constant work of living organisms. This is the classic biosignature, and it is a good one, but it is also deeply provincially Earth-centric. We are searching for life as we know it. What if life elsewhere has a completely different chemical toolkit? Webb is already forcing us to expand our thinking. On the super-Earth K2-18b, a planet about 8 times the mass of our own, the telescope recently detected the tantalizing, deeply controversial signal of dimethyl sulfide. On Earth, this molecule is produced almost exclusively by marine phytoplankton. It is a biological waste product, a molecule that screams life. But the detection on K2-18b is at the absolute edge of the instrument's capability. It is a whisper, not a shout. It could be real, it could be noise. But the fact that we are even having this conversation, that Webb can see a molecule that is produced by microscopic algae swimming in an ocean 124 light-years away, is nothing short of a revolution. Yet even here, the chemistry is breaking the rules. K2-18b is not a perfect Earth analogue. It is a Haitian world, a theoretical class of planet with a hydrogen-rich atmosphere and a global liquid water ocean. When the models were first run for Haitian worlds, they predicted a stable, predictable chemical environment. But the data from Webb shows clear signs of chemical disequilibrium there as well. The ratios of carbon dioxide and methane are off. The atmosphere is doing something the models cannot explain. And the presence of dimethyl sulfide, if confirmed, would mean that a biological source is actively pumping this molecule into the sky faster than it can be destroyed by the star's ultraviolet light. This is the smoking gun. This is the kind of imbalance that screams life. But we have to be careful. There is a seductive danger in this work. Every mystery is not a sign of aliens. The universe is perfectly capable of surprising us with purely geological or chemical processes we have never seen before. The sulfur dioxide on WASP-39b was a surprise, but it was not biology. It was a weird, unexpected photochemical reaction. The missing water on some worlds could be caused by an unappreciated sequestration mechanism, where water is locked away deep in the planet's mantle, never reaching the atmosphere. The excess carbon could be a relic of a chaotic planetary migration, where a world formed far from its star in a freezing, carbon-rich region of the protoplanetary disk, and then spiraled inward. This is the fundamental tension at the heart of modern exoplanet science. We are collecting data so far beyond our predictive capabilities that every new observation is both a revelation and a humiliation. We are like a child who has just been handed a master key to a vast library, only to realize we cannot read the language the books are written in. We can decode the letters. We can measure the wavelengths. We can identify the molecules. But understanding the story they tell, understanding the dynamic, living, breathing system that produced them, that is a vastly harder challenge. And there is another layer to this, a terrifying one. Webb is now looking at planets that are not just hot Jupiters or super-Earths. It is looking at temperate, rocky worlds in the habitable zones of small, dim red dwarf stars. These are the most common type of star in the galaxy and the most promising places to search for life. But the atmospheres of these worlds are being bombarded by stellar flares, high-energy particles, and intense ultraviolet radiation. The models predicted that these atmospheres should be stripped away, leaving barren, airless rocks. But the initial data is suggesting something else. Some of these planets appear to have retained surprisingly thick, stable atmospheres. They have held on to their air against all odds. This is a massive rule break. If the models are wrong about basic atmospheric retention, then the entire habitable zone estimate, the very concept of where life can exist, has to be recalibrated. The history of science is a graveyard of confident predictions. The geocentric model was confident. The ether was confident. The steady-state universe was confident. And now our models of exoplanet atmospheres are joining that graveyard. Every time Webb turns its gaze to a new world, it is a test. And so far, the test results are coming back with a single universal letter grade. Not yet understood. We are standing at the edge of a vast, unknown chemical landscape. The periodic table is the same everywhere, but the recipes are not. The rules of quantum mechanics are fixed, but the planetary cookbooks are written in a language we are only beginning to decipher. The universe is not broken, our models are, and that is not a failure. It is the beginning of a deeper truth. Webb has cracked open a doorway. Every strange spectrum, every unexpected molecule, every impossible cloud of vaporized rock is a gift. It is the universe telling us to stop guessing and start listening. The radius gap, the Fulton gap, a hole in the data so clean, so stark, that for years it felt like a cosmic joke. Kepler found thousands of planets, tens of thousands of candidates, and yet, when you plotted them all out by size, there was this bizarre, almost surgical absence. Planets between 1.5 and 2.0. Earth radii were vanishingly rare, almost non-existent. It was like looking at a bookshelf where every single book between 5 and 6 inches tall had been quietly removed. Not by a librarian, by nature itself. And for a long time, we thought we knew why. The reigning hypothesis was photoevaporation. Here is how it works. A young planet forms with a thick, puffy atmosphere of hydrogen and helium. It sits close to its star, getting blasted by extreme ultraviolet and X-ray radiation, XUV as it is called. That radiation acts like a cosmic blowtorch. It heats the upper atmosphere, and that gas bleeds off into space. Over hundreds of millions of years, a planet either loses almost all of its atmosphere, shrinking down below 1.5 Earth radii, or it holds on to enough mass to survive, staying above 2.0. You do not get to hang around in the middle. The physics does not allow it. It is an evolutionary funnel. You either shrink or you stay big. There is no stable in between. That was the theory. And it was beautiful. It explained the data perfectly. Until Webb looked directly into the gap and found planets sitting right there, right inside that missing size range. As if they had read the textbook and decided to ignore it. These planets should not be stable. They are in the exact size range where photoevaporation should be actively stripping their atmospheres. They should be shrinking, losing mass, transitioning out of the gap. But Webb sees them persisting. They are just sitting there, calm, defiant, challenging everything we thought we understood. So what gives? One possibility is that the photoevaporation model is not the whole story. Enter the alternative, core-powered mass loss. This is a different kind of beast. It says you do not need a star to blow the atmosphere off. The planet can do it itself. Think about it. When a planet forms, it is a hot, molten ball. It has a massive amount of internal heat left over from its formation. That heat slowly radiates outward over billions of years. And as it escapes, it pushes against the planet's own atmosphere from the inside. Internal heat flow creates a slow, steady outgassing. The planet literally evaporates its own air, heating itself from the core and venting its own atmosphere into space like a geological sigh. Here is where Webb gets crafty. It looked at these gap planets and mapped their thermal emission. The heat escaping from them is not behaving the way models predicted. We see hot spots on the night side, the side facing away from the star. In a normal world, the night side should be cold, but Webb is finding patches of unexpected warmth. That suggests interior heat flow is much more complicated than we assumed. Something deep inside these planets is pumping energy out in ways our equations have not accounted for. The gap planets are not just survivors. They might be rewriting the rules of planetary evolution. And this ties directly into one of the biggest questions in exoplanet science. The split between super-Earths and mini-Neptunes. These two populations are supposed to be fundamentally different. A super-Earth is a rocky world, maybe with a thin atmosphere, maybe none at all. A mini-Neptune is a small gas giant with a thick hydrogen-helium envelope and no solid surface you could stand on. They are different beasts with different origins. Yet they overlap in size. A planet at 1.5 Earth radii could be a rocky super-Earth with no air, or it could be a mini-ice giant with a crushing atmosphere. You could not tell them apart just by looking at their radius. You had to guess. Webb ended the guessing. By measuring density, composition, and most importantly, atmospheric signatures, it can now tell you exactly which is which. And the results are shocking. Some super-Earths planets we assumed were bare rock have retained vast hydrogen envelopes. Puffy atmospheres that should have been stripped away billions of years ago. They are still there, still puffy, still defying the age of the star. How they hold on to that gas is a mystery. It should have boiled off into the vacuum. But the data is clear. They kept it. Then there are the outliers, the worlds that do not fit any category we have. Take TOI 1452b. This is a candidate for a water world, not a planet with oceans on the surface. A planet that is mostly ocean. Estimates suggest that up to 70% of its mass could be liquid water. That is not a water world. That is a water planet. A global ocean potentially hundreds of kilometers deep. No land, no sea floor that you could reach. Just an endless, dark, high-pressure ocean beneath a steamy atmosphere. The ocean world paradox is that too much water might be terrible for life. Think about it. Earth's thin ocean layer is ideal because it creates chemical gradients. You have different environments at different depths, different temperatures, different salinities. Life thrives on those boundaries. But on a world that is mostly water, the chemistry goes wrong. The pressure at the bottom is crushing, and the lack of exposed rock means there is no way to cycle nutrients. The ocean becomes a uniform, stagnant chemical soup, with no gradients for life to exploit. Too much water is not a paradise, it is a dead end, and Webb is finding more and more of these paradox worlds. Puffy gas giants with densities lower than styrofoam. WASP-17b is a perfect example. It is so low density that it should not be gravitationally stable. It should be tearing itself apart, or at least collapsing into a more compact form. But it just sits there, fluffier than cotton candy, coasting through space like a cosmic balloon. The radius gap was supposed to be a dividing line between planet types, a hard boundary that separated rocky worlds from gaseous ones, a rule carved into the architecture of planetary systems. But Webb looked at that line and found it is more like a suggestion, a gentle recommendation. And planets are ignoring it. The implications of these findings are rewriting the textbooks in real time. We are now forced to reconsider the very definition of a planet's habitable zone. For decades, we defined it as the orbital distance where a planet could have liquid water on its surface. That was a geometric calculation based on stellar flux. You plug in the star's luminosity, calculate the distance where water freezes and where it boils, and draw a thin Goldilocks band around the star. That was the habitable zone. It was simple, it was elegant, and it was almost certainly wrong, because a planet's size and internal composition matter just as much as its orbital distance. A mini Neptune with a thick hydrogen envelope might have a habitable zone much closer to its star. The hydrogen envelope acts like a blanket, trapping heat and raising the surface temperature even when the star is dim. Conversely, a super-Earth with no atmosphere might need to be much closer to its star just to keep water from freezing solid. The radius gap is not just a physical divide, it is a biological divide. It separates worlds that might host life from worlds that almost certainly cannot. And Webb is now showing us that the line between those two categories is fuzzy, dynamic, and full of exceptions. Consider the case of the TRAPPIST-1 system. 7 Earth-sized worlds orbiting an ultra-cool dwarf star. This was the holy grail of exoplanet hunting. 3 of those planets orbit in the classical habitable zone. They are exactly the right distance for liquid water. But Webb looked at them and found something deeply troubling. The innermost planets are likely bone dry. Their surfaces are baked and irradiated. They may have lost all their water to space billions of years ago. The outermost planets might be frozen solid, locked in a permanent ice age, because the star is too dim to keep them warm. The habitable zone in that system might be a ghost zone, a mathematical illusion, with no actual habitable planets inside it. And then there is the question of atmospheric chemistry. Webb has found molecules in exoplanet atmospheres that we did not expect: carbon dioxide, water vapour, methane, and in one stunning case, dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton. It is a biological signature, a biosignature. When the data came in for that particular world, the K2-18b candidate, the scientific community held its breath. A temperate mini-Neptune orbiting a red dwarf with water clouds in its atmosphere and a potential chemical marker of life. But here is the cruel twist. The radius gap tells us that K2-18b is exactly the kind of world that should not be in a stable evolutionary state. It sits at the upper edge of the gap, around 2.6 Earth radii. It is a mini-Neptune with a thick atmosphere. It is the kind of world that might have no surface at all. An ocean world with a crushing hydrogen envelope. A planet where the pressure at the so-called surface is so high that water turns into a supercritical fluid, not liquid, not gas, a strange alien state where the molecules are too energetic to stay liquid, but too dense to float away as vapor. If life exists there, it is not life as we know it. It is life swimming in a hot, high-pressure chemical soup beneath a hydrogen sky. It is life that has evolved on a world that defies the radius gap, that persisted where photoevaporation should have stripped it bare. And that is the final lesson Webb is teaching us. The universe does not care about our categories. The radius gap is not a rule. It is a pattern, a statistical trend that emerges from a sample of thousands of planets. But when you zoom in on individual worlds, the pattern breaks. Every planet is its own experiment, its own history, its own set of chaotic collisions and orbital migrations and atmospheric losses. We thought the gap was a wall, a solid barrier between super-Earths and mini-Neptunes, between rocky worlds and gaseous ones, between lifeless rocks and potential biospheres. But Webb has shown us that the wall is full of doors, and some of those doors are opening onto worlds we never imagined could exist. Worlds that hold onto their atmospheres against all odds. Worlds that are mostly ocean. Worlds that are puffier than physics should allow. The radius gap is not the end of the story. It is just the beginning. And Webb is only scratching the surface. Every new observation, every new spectrum, every new temperature map is throwing another brick out of the wall we built for ourselves. The gap is closing, but only because our ignorance is finally being filled with data. And that brings us to the really strange stuff. The orphans, the drifters, the worlds that have no sun. We call them rogue planets, and before James Webb came along, we thought they were a cosmic oddity, a freak accident, a handful of planetary misfits that got kicked out of their solar systems and sent wandering into the void. But Webb has shattered that assumption completely. What we are now realizing is that these lonely wanderers might not be the exception. They might be the rule. Let me define exactly what we are talking about here. A rogue planet is a planetary mass object that drifts through space with no host sun. It has no parent sun to orbit, no source of stellar light. It is completely alone, travelling through the infinite darkness of interstellar space, possibly for billions of years. We knew they existed before Webb, of course. We had a few tantalizing hints here and there, but they were considered rare. The standard models suggested that only a tiny fraction of planets would ever get ejected from their systems. Maybe 1 in 1,000, maybe 1 in 10,000. Nothing to get excited about. Then Webb looked at the Orion Nebula. In October of 2023, astronomers released the results from a deep survey of this star-forming region, and the numbers were absolutely jaw-dropping. In a single field of view, Webb detected 540 planetary mass objects. Not stars, not brown dwarfs, planetary mass objects. And here is the kicker. Many of these objects showed no evidence of being gravitationally bound to any star. They were just floating there, hundreds of them, clustered together in this vast nursery of newborn worlds. This was the largest single-release rogue planet catalogue in human history, and it did not just confirm the existence of rogue worlds. It completely rewrote our understanding of how common they actually are. So how do these orphaned worlds come to exist in the first place? There are two main pathways, and they are fundamentally different in nature. The first one is the ejection pathway. This is the classic model. A planet forms in a young solar system. orbiting its star, and over time, gravitational interactions with other planets, or maybe a passing star fling it out. It gets slingshotted away, never to return. This is what we used to think happened to every rogue planet. And under this model, rogue planets should be relatively small. Why? Because smaller planets are easier to eject. A massive Jupiter-sized world has a lot more gravitational inertia. It is harder to kick out. So the ejected rogues we expected to find were mostly Earth-sized or smaller, maybe the size of Mars or Mercury, just little rocky worlds cast adrift. But Webb has shown us something completely different. The 540 objects in Orion include plenty of worlds that are Jupiter-sized or even larger. These are not small ejected stragglers. These are massive giants that never had a star to begin with. And that brings us to the second pathway, the formation pathway. Some rogue planets may simply form the same way stars form. They condense directly out of clouds of gas and dust, but they never accumulate enough mass to ignite nuclear fusion. They are failed stars, brown dwarfs technically at the upper end. But at the lower end, these objects are indistinguishable from giant planets in every way except that they never had a parent star. They just formed alone, in isolation, and there they remain. This changes everything. Because if rogue planets can form independently, and if they are as common as Webb is suggesting, then the sheer number of them in our galaxy is staggering. Let me put it in perspective for you. We have known for a long time that the Milky Way contains somewhere between 100 and 400 billion stars. That is a lot. But gravitational microlensing surveys, which study how light bends around massive objects, have begun to give us estimates for the rogue planet population. And the numbers are genuinely shocking. There could be as many as 100 billion rogue planets in the Milky Way alone. That is, more free-floating planets than there are stars. Let that sink in for a moment. There could be more sunless worlds drifting through the darkness of interstellar space than there are suns themselves. That fundamentally changes how we think about galactic population statistics. When we talk about the most common type of planetary body in our galaxy, we might not be talking about Earths or Mars or even Jupiters. About rogues. Now, here is a question that keeps planetary scientists up at night. Could these rogue planets actually be habitable? And I do not mean habitable in the traditional sense, obviously. There is no sunlight, no photosynthesis, no warm days under a yellow sun. But life does not necessarily need starlight to survive. We have already found entire ecosystems thriving in the darkness of Earth's deep ocean trenches, relying on geothermal heat instead of the sun. Rogue planets could work the same way, but on a much larger scale. If a rogue planet has a thick, insulating atmosphere and a hot, active core, it could maintain a subsurface ocean for billions of years. Radioactive decay in the planet's mantle generates heat. Internal geological processes churn that heat upward, and under a thick shell of frozen ice, the water remains liquid. No star required, no sunlight needed, just a warm core and a blanket of ice. This is not science fiction. We have evidence of exactly this kind of world right here in our own solar system. Europa, Enceladus. The subsurface oceans of these moons are heated by tidal forces and radioactive decay, and they exist in the complete absence of sunlight. A rogue planet drifting alone for billions of years could have the same internal heat sources, and that heat could keep liquid water stable beneath its frozen crust. We are not just talking about a few puddles here. We are talking about global oceans hundreds of kilometers deep, wrapped around a rocky core, warm and dark, and stable for the entire lifespan of the galaxy. And then there is the panspermia implication. If rogue planets can hold life, could they also transport life? Think about it. A rogue planet that forms in a living solar system, or that passes through one, could pick up microbial hitchhikers, bacteria embedded in the ice, spores locked in the crust, and then that planet drifts away, carrying its biological cargo across the void. Over millions of years, it could wander into another solar system, pass near another star, and seed that system with life. This is not wild speculation. We know that rocks from Mars have reached Earth. We know that material can be exchanged between planets. So why not between whole systems? Rogue planets could be the great cross-contamination agents of the galaxy, carrying biology from star to star on a timescale that dwarfs human civilization. We have seen some truly bizarre examples of these orphaned worlds up close, thanks to Webb's infrared imaging. Specifically, there is a class of objects called JUMBIOs. JUMBIO stands for Jupiter Mass Binary Objects. These are pairs of rogue planets drifting together through space, locked in mutual orbit. No star, no third body, just two planetary mass objects circling each other in the darkness. And Webb's detailed observations have shown something deeply puzzling. These JUMBIOs are warmer than expected. Their internal temperatures are higher than any model predicted. They have active internal heat sources that seem to be running strong even billions of years after formation, and we do not know what is powering them. The current models for planetary cooling suggest that a Jupiter-sized object formed in isolation should cool down relatively quickly. After a few 100 million years, it should be cold, dead. But the jumbos are not cold. They are radiating significant amounts of heat. Something is generating that energy deep inside them, and it is not nuclear fusion. It is not stellar ignition. It is an unknown mechanism. Some researchers have proposed that these objects might have formed unusually fast, with massive amounts of gravitational potential energy still locked in their interiors. Others have suggested that they might be capturing energy from passing magnetic fields or cosmic radiation. But the truth is, we do not have a good explanation yet. And then there is the orbital problem. How do two planetary mass objects end up in a stable binary orbit around each other with no third body involved? Gravity does not work that way easily. For two objects of similar mass to capture each other in a bound orbit, you typically need a third object to steal away some of the kinetic energy. It is a gravitational dance that requires an intermediary. So where did the third body go? Was there originally a star that was ejected? Was there a larger planet that got pulled away? Or did these binary pairs form together directly from the collapsing gas cloud as a kind of mini star system without the star? The mathematics are still being worked out, and the answer is far from clear. We have also found evidence that some rogue planets possess strong magnetic fields. They show signs of auroral radio emission, the same kind of radio waves that Jupiter generates when its magnetic field interacts with charged particles. These emissions require an internal dynamo, a churning conductive fluid core that generates a magnetic field. And that means these orphaned worlds are not dead rocks. They are geologically active. They have hot, liquid interiors. They have magnetic fields that could protect a subsurface biosphere from cosmic radiation. They have everything a world needs to support life except a star. So here is where we are. If rogue planets are this common, if they number in the hundreds of billions in our galaxy alone, then the old formulas for calculating the probability of extraterrestrial life need a serious update. The Drake equation, the famous formula that estimates the number of intelligent civilizations in the galaxy, has never included rogue planets. It assumed every life-bearing world needed a star. But that assumption is dead. Rogue planets are everywhere. They have internal heat. They have liquid water. They have magnetic fields. And they can carry life across the galaxy for billions of years. Life could exist on billions of worlds that we have never considered because they have no star. And Webb is just beginning to show us that these worlds are not rare exceptions. They are the majority. The darkness is not empty. It is teeming with orphans, and so we find ourselves standing at the edge of a new frontier. The orphan worlds in the dark are one thing. Fascinating, yes, provocative, absolutely. But the question that has haunted humanity since we first looked up at the stars is not just about planets. It is about life. And that brings us to the most thrilling and most treacherous hunt in modern astronomy: the search for biosignatures. Now, let's be clear about what we mean when we say biosignature. It sounds technical, but it is beautifully simple. A biosignature is any chemical or physical signal that implies biological activity. It is a clue, a fingerprint, something in the light coming from a planet that says, with a little luck and a lot of evidence, that something is alive there. But here is the catch: it has to be detectable remotely. We cannot send a rover to these worlds. We can only catch their light. And before the James Webb Space Telescope, that light was nearly impossible to read for anything this specific. Webb changed everything. It changed what we can detect from trillions of miles away. Suddenly, the whispers in that faint light became louder, but whispers can be deceiving. This is where the trouble begins. Not all that glitters is gold, and not every chemical signal is proof of life. The universe is a master of deception. Geological and photochemical processes can mimic biology perfectly. They are the universe's greatest illusionists. For example, oxygen. We tend to think of oxygen as the hallmark of life. We breathe it. Plants make it. So surely, if we see oxygen in an exoplanet's atmosphere, we have found life, right? Not so fast. Oxygen can be produced abiotically. That is a fancy way of saying it can be made without any living thing. Ultraviolet light from the parent star can break apart carbon dioxide molecules, releasing oxygen. No microbes, no plants, just physics and chemistry. The star itself can do what we thought only life could do. So, oxygen alone is a terrible biosignature. It is a trap, a false positive. That is why the scientific community reacted with extreme caution to one of the most explosive claims of the last few years. You might remember the headlines about K2-18b. That is a planet in the habitable zone of its star, and a team of researchers announced that they had detected dimethyl sulfide in its atmosphere. Dimethyl sulfide is a molecule that, here on Earth, is almost exclusively produced by marine algae. It is a biological product. If you smell that rotten cabbage-like odour near the ocean, that is dimethyl sulfide. So, seeing it on a distant world would be a bombshell. It would be the strongest evidence yet for extraterrestrial life. But the reaction from the wider scientific community was not celebration. It was skepticism. The signal was weak, extremely weak. It was hovering right at the edge of what Webb can even detect. When a signal is that faint, alternative interpretations are not just possible. They are probable. Maybe the data reduction was flawed. Maybe it was noise. Maybe it was a statistical ghost. The team that made the claim knew this. That is why they used careful language. But the headlines did not. So, what happened next? Follow-up observations of K2-18b are ongoing right now as we speak. More data is flowing in. And here is the beautiful, agonizing thing about science. More data either strengthens the signal or kills it. There is no middle ground. The initial paper from 2023 was always labelled as preliminary. It was a first look, a hint, a maybe. The full confirmation or the full refutation is expected sometime around 2025 or 2026. That is barely a blink from now in the timeline of astronomy. We are living through the most crucial moment in the search for life, and we do not even know the answer yet. But K2-18b is not the only game in town. Far from it. Let us talk about the system that keeps every astronomer awake at night, TRAPPIST-1. 40 light-years away, a dim red sun hosts 7 rocky worlds. 3 of them, E, F, and G, sit squarely in the habitable zone. TRAPPIST-1e, and 1F in particular, are the most Earth-like candidates we have ever found. They are roughly the same size as Earth. They have the right mass. They are at the right distance from their star to have liquid water on the surface. If there is life anywhere near us, it is probably there. But here is the maddening truth. Webb has not fully characterized them yet. Not even close. It takes time. To really study an atmosphere, you need to catch the planet as it transits across its star. The starlight filters through the atmosphere and the molecules in that atmosphere leave their fingerprints in the light. But one transit gives you almost nothing. You need dozens of transits. To build up enough signal, you have to watch the same planet cross the same star over and over again. And the TRAPPIST-1 system is small and fast, but it is still a painstaking process. We are talking years of observation, but Webb has already given us a taste of what is coming. It observed TRAPPIST-1b, not one of the habitable zone planets, but the innermost world, a scorched rock, and it found something completely unexpected. Webb measured the thermal emission from that planet. That is the heat coming off the surface, and what it saw was asymmetry. The east side of the planet was significantly hotter than the west side. That sounds like a small detail. It is not. That temperature difference suggests that the planet has an atmosphere that is redistributing heat. The heat is moving from the day side to the night side, and that movement means one thing. There is an atmosphere doing the moving. So, even on a world that is too hot for life, Webb is finding atmospheres. That is a huge clue for the cooler planets further out. Now, let us come back to the hunt for biosignatures and confront the single most frustrating problem in astrobiology. It is called the oxygen paradox. Imagine this: Webb squints at TRAPPIST-1e, and after months of analysis, the data comes back. There is oxygen, a lot of it. The headlines would explode, humanity would celebrate, but the scientists would not, because oxygen by itself is not proof. As I mentioned, ultraviolet light can make it. But there is another, more subtle way oxygen can build up on a planet without life. It is called hydrogen escape. If a star is active, it can strip hydrogen from a planet's atmosphere. Water gets broken apart by the star's radiation. The hydrogen escapes to space. The oxygen is left behind. It accumulates. You can end up with a planet that has a thick oxygen atmosphere, but no biology. Just a dead world slowly losing its oceans to its own sun. The chemistry looks like life, but it is a ghost. So, what is the solution? The combination strategy. Scientists are no longer looking for a single smoking gun. They are looking for a constellation of evidence. The Holy Grail is a detection of oxygen, methane, and nitrous oxide all together in the same atmosphere. That combination is almost impossible to explain without life. There is no known geological process that can produce all three simultaneously in the quantities we would detect. Oxygen and methane together are already a strong hint, because they react with each other and need to be constantly replenished. Geologically, that is hard to do without biology. But add nitrous oxide to the mix, and you have something truly special. Nitrous oxide, laughing gas. It is a molecule most of us associate with a dentist's office, but on Earth, nitrous oxide is produced almost entirely by microbes in the soil and the oceans. It is a byproduct of their metabolism. In 2022, a paper came out that shook the field. It argued that nitrous oxide might be one of the most overlooked biosignatures in existence. It is easier to detect than some other molecules, and it is far less ambiguous than oxygen alone, because the geological pathways to produce significant amounts of N2O are incredibly rare. If Webb sees nitrous oxide in an exoplanet's atmosphere, the chances that it comes from life jump dramatically. So, when will we know? When will we have a confirmed biosignature? The honest answer is the one most researchers give. 10 to 20 years minimum. That is the cautious estimate. But here is the thing. Webb has already shortened that timeline. Before Webb launched, the most optimistic predictions put a confirmed detection at 50 to 100 years away. Now the conversation has shifted. The optimistic end is the 2030s. That is not a lifetime away. That is next decade. That is within reach for most of us listening right now. We are closer to answering the oldest question, are we alone, than any generation in human history. But Webb is showing us that the answer will not be simple. It will not be a clean yes or no. It will be layered. It will require patience. It will demand that we learn to read the faintest traces of light across the endless dark, and it will require us to accept that even when we find that signal, the debate will not end. It will only begin. What the models got wrong, and why for decades, we thought we understood how planetary systems form. We built our models on the foundation of our own solar system, assuming it was the template, the standard, the blueprint that all other systems would follow. But the James Webb Space Telescope has done something remarkable. It has not just taken beautiful pictures, it has shattered that blueprint, and what we are left with is a universe that is far stranger, far more chaotic, and far more creative than our physics textbooks ever predicted. Let's start with the NICE model. Named after the French city where it was developed, it proposed something radical. It suggested that the planets in our solar system did not form where we see them today. They migrated, dramatically. In the early days, Jupiter and Saturn, the gas giants, moved inward, plunging toward the Sun, before reversing course and migrating outward again. This motion, this gravitational dance, disrupted everything. It scattered comets, rearranged the asteroid belt, and shaped the solar system we know. For a long time, this was considered a possible explanation for our own peculiar cosmic neighborhood. But Webb has shown us that planet migration is not just a possibility, it is universal. Every large planet, it seems, moves significantly during its formation. What Webb sees today, when it points its mirrors at distant star systems, is not where those planets formed. It is where they ended up after millions of years of chaotic movement, after being pushed and pulled by the gravity of their siblings and the disk of gas and dust that surrounded their young star. This brings us to the Grand Tack hypothesis for our solar system. The name itself is evocative. It imagines Jupiter, the king of planets, performing a maneuver like a sailing ship tacking against the wind. In this hypothesis, Jupiter plunged inward, all the way to where Mars now orbits. It swept through the inner solar system, scattering smaller bodies, before some gravitational interaction with Saturn caused it to reverse course and retreat to its current position. This violent migration explains two long-standing puzzles. First, the asteroid belt. It is not a single, dense ring of rock. It is a sparse, broken band. The Grand Tack explains that Jupiter's passage scattered most of the material that should have formed a planet there. Second, it explains why Mars is so small. Mars should have been a much larger world, but Jupiter stole its building material, leaving it a runt, a fraction of its expected size. But here is the implication that keeps planetary scientists up at night. If our solar system required such a specific, even unusual, migration pattern to form, then our system might not be the template. It might be the exception. It might be the weird kid in the cosmic family. And then we look at what Webb has revealed about hot Jupiters. These are gas giants that orbit their stars in mere days, hugging them impossibly close. The traditional model said they formed far out, in the cold regions of their disks, and then migrated inward, slowly, over millions of years. But Webb's observations show that this migration is faster, much faster. Some of these hot Jupiters appear to be caught in the act of migrating right now, over human timescales. We are watching them inch closer to their stars in real time. Something the models said should be almost impossible to detect. It is like watching a glacier race down a mountainside. It changes everything we thought we knew about the speed of planetary evolution. This forces us to confront a fundamental question in planetary science. How do gas giants even form in the first place? There are two competing theories. The first is core accretion. In this model, a solid core of rock and ice forms first, growing slowly as dust particles stick together. Once this core reaches a critical mass, about 10 times the mass of Earth, its gravity begins to pull in a massive envelope of gas from the surrounding disk, creating a gas giant. This process is slow. It takes millions of years. The second theory is disk instability. In this model, the gas and dust disk itself becomes gravitationally unstable. and parts of it collapsed directly into a planet, like a star forming. This is fast. It can happen in a few thousand years. For decades, astronomers argued over which was correct. Webb, with its incredible resolution, looked at young protoplanetary disks, hoping to settle the debate. And what did it find? A mess. The data does not cleanly favour either model. Instead, it suggests both may operate depending on the specific conditions of the disk. Some planets form slowly, by accretion. Others form fast, by collapse. The universe once again refuses to pick a side. This brings us to the minimum mass solar nebula. This is a concept. It is the hypothetical amount of material, the minimum mass of gas and dust that must exist in a disk to build a planetary system like our own. It is a baseline, a starting point for our models. But when Webb studied dozens of young star systems, it found something deeply troubling. Many of these systems appear to have far less disk material than the minimum required. They are starved. They are deficient. And yet, planets have formed anyway. It is like looking at a construction site with a pile of bricks that is 1/10 the size it should be, and seeing a skyscraper already standing. Something is missing from our understanding. Either planets are far more efficient at gathering material than we thought, or the initial mass of the disk was much higher, and has since been lost. And then there is the dust-to-gas ratio problem. In a typical protoplanetary disk, you expect a certain ratio of solid particles, the dust, to gas, mostly hydrogen and helium. But Webb has found disks where this ratio is wildly skewed. Some disks have too much solid material and too little gas. This implies that the gas is being lost rapidly early in the disk's life, blown away by the star's radiation or powerful winds. But here is the paradox. Planets are still forming in these disks, even without sufficient hydrogen to build a massive gas envelope. It suggests that the window for planet formation is narrow and fierce, and that planets are being built under conditions of extreme scarcity. They are survivors, scrabbling together whatever material they can find. Perhaps the most beautiful and perplexing discovery from Webb involves resonance chains. These are orbital configurations where multiple planets are locked in precise gravitational relationships. For example, for every 2 orbits the innermost planet makes, the next planet makes exactly 1, or 3 to 1, or 4 to 2. It is a celestial dance, a mathematical harmony. The TRAPPIST-1 system, with its 7 Earth-sized planets, is the most famous example. But Webb has found that these resonance chains are far more common than predicted, and they are more precise. The gravitational tuning is impeccable. It suggests that planets form in a very orderly, synchronized way early on, and that this order can be preserved for billions of years. It is a counterpoint to the chaos of migration, a hint of underlying structure in the apparent madness. This brings us to the crisis at the heart of planet formation theory, the timescale. Standard core accretion needs roughly 10 million years to build a Jupiter-sized planet. But Webb is looking at protoplanetary disks that are only 1 to 2 million years old, and it sees fully formed planets in them, giant planets. The models say this should not be possible. It is like finding a fully grown adult in a kindergarten classroom. Something is building planets radically faster than our theories allow. And this is where the streaming instability comes in. This is a relatively new idea, a mechanism that might solve the crisis. It works like this. As dust particles drift through the gas of the disk, they can concentrate into dense, clumpy clouds. These clouds become gravitationally unstable and collapse directly into large planetesimals, skipping the slow, step-by-step accretion phase. It is a shortcut. It bypasses the bottleneck, and it could explain the impossible young planets that Webb is finding. The streaming instability allows planet building to happen in a cosmic blink of an eye. So, here we are. The models were not wrong because they were bad science. They were wrong because the universe is more creative than physics textbooks allowed. We came into this era with clean equations and elegant theories. And Webb has handed us a universe that is messy, chaotic, and full of surprises. It has shown us that planets can form too fast, in disks too small, with the wrong mix of materials. It has shown us that migration is universal, that resonance is common, and that our own solar system may be the exception, not the rule. It has forced us to accept that we are not the centre of this story. We are just one strange, beautiful chapter in a book that is still being written, and in the end, that is the most humbling and exhilarating realization of all. The idea that Earth is special has always been a hard sell in science. For centuries, we clung to the Copernican principle, the comforting notion that our place in the universe is nothing out of the ordinary. We are not special, the thinking went. We are average. We are the rule, not the exception. But Webb is turning that idea on its head. Every single new discovery, every strange world it finds that defies our models, whispers a different story. It whispers that maybe, just maybe, we are the weird ones. Our solar system, with its neat, orderly arrangement of rocky inner planets and gas giants far from the sun, is looking less like a template and more like a statistical fluke. We are looking at other systems and seeing chaos. We see super-Earths crammed impossibly close to their stars. We see mini-Neptunes orbiting in what should be the scorched zone. We see gas giants on wildly elongated orbits that should have been ejected long ago. None of it looks like our neighbourhood. And that forces a question that makes cosmologists uncomfortable. What if Earth is the outlier? What if we are not the model for how a life-bearing planet works, but a strange, fragile exception in a universe that is mostly hostile to everything we consider normal? This is the heart of the rare Earth hypothesis, and Webb is putting it on trial. The hypothesis suggests that complex life is incredibly rare because it requires an insane number of lucky breaks. You need a stable star. You need a planet the right size, with plate tectonics, a magnetic field, a large moon to stabilize the axial tilt, the right distance from the sun, the right atmospheric composition, and 1 billion years of uninterrupted geologic stability. It is a staggeringly long list. For decades, scientists have argued over which of these conditions are truly essential. Webb is now providing the first real test. When it finds a planet with the right combination of atmospheric gases, like oxygen and methane, in a system that is wildly chaotic, it weakens the rare Earth hypothesis. It suggests life can survive in places we thought were impossible. But when Webb finds a perfect candidate for a habitable planet, a world in the sweet spot with liquid water on the surface, and then sees nothing there, no biosignatures, no chemical imbalance, just dead rock, that strengthens the case for rarity. It tells us that the right conditions are not enough. Something else is missing. And right now, the data is pointing both ways. It is a split decision. We are caught between two possibilities, and we do not yet know which one is true. But the mere fact that we are having this debate, that we are using actual data to test this hypothesis, is a revolution in itself. Webb is also shattering one of the most cherished concepts in astronomy, the habitable zone. For years, we have defined the habitable zone as that narrow band around a star where liquid water can exist on a planet's surface. It is a simple, clean, easy-to-understand concept. But Webb is showing us that the universe does not care about our simple categories. It is finding planets with atmospheres so thick and toxic that the surface is a pressure cooker at 1,000 degrees, yet the upper atmosphere might be temperate. It is finding icy worlds far outside the zone that have subsurface oceans heated by tidal forces. It is finding worlds like Titan. Titan is a moon in our own solar system, a world with a thick nitrogen-rich atmosphere, a complex organic chemistry, and lakes of liquid methane and ethane on its surface. There is no liquid water. The surface is minuscule 180 degrees Celsius, but it has weather, rain, rivers, and a hydrological cycle, just with methane instead of water. And Webb is now finding exoplanets that look just like Titan. These are worlds with nitrogen-dominated atmospheres, with organic hazes, and no sign of water vapour at all. They are impossible planets by the old definition of habitability. But what if life can exist there? What if hydrocarbon lakes are just as good as water oceans for certain types of exotic biology? We have no idea. But Webb is identifying the candidates. It is giving us a target list of worlds where life could be fundamentally different from everything we know. And that changes the entire game. If life can exist on a Titan-like world, then the number of potentially habitable planets in the galaxy just exploded from millions to billions. And this brings us directly to the most haunting question in all of science, the Fermi paradox. If planets that should not exist are everywhere, if life could potentially arise in so many different environments, if the galaxy should be teeming with biology, then where is everybody? The cosmic silence becomes even more deafening. Webb is not finding signals. It is not finding alien megastructures. It is not finding artificial atmospheric pollutants. It is finding dead planets and weird chemistry, but nothing that screams intelligence. So we are left with three terrible options. The first is that life is truly rare, that the leap from chemistry to biology is the hardest step in the universe, and we are the only ones who made it. The second is that life is common, but intelligence is self-destructive. That every civilization eventually hits a technological ceiling and wipes itself out. The third is that life is out there, but we are too blind to see it. We are listening with the wrong instruments. We are looking for the wrong signatures. We are trapped in our own biological and technological adolescence. Webb is making all three of these options equally plausible. It is not solving the Fermi paradox. It is deepening the mystery. And that is, in its own way, the most profound discovery of all. And let us be clear about something. Webb was supposed to last 10 years. That was the original mission design. 10 years of fuel, 10 years of science. But the launch was so perfect, so precise, that it saved an almost unimaginable amount of fuel. Current estimates now suggest that Webb has enough propellant to operate for more than 20 additional years. We are looking at a telescope that could still be sending us data in the year 2040, and perhaps beyond. It has already exceeded every mission goal. It has rewritten entire chapters of astronomy. And it is barely a few years into its operational life. The second life of Webb has only just begun. But even as we marvel at this machine, the next generation is already on the drawing board. The Habitable Worlds Observatory is scheduled for launch in the 2040s. It is a telescope designed for one single purpose. It will directly image Earth-like planets around Sun-like stars. It will photograph their surfaces. It will analyse their atmospheres for the faintest signatures of life. Webb is the scout. H, where will be the settlement. Webb is showing us where to look. H, where will tell us what is actually there. Everything we are learning now is just the warm-up act. The real show is still a generation away. The paradigm shift happening right now is deeper than any single discovery. It is a fundamental rewriting of our understanding of planetary science. Textbooks published before 2022 are already outdated. University courses are scrambling, adding new modules, throwing out old models, trying to keep up with a torrent of data that is moving faster than the curriculum can be updated. Students today are learning things that their professors did not know 2 years ago. That is unprecedented. And yet, for all that Webb has revealed, there are massive blind spots. There are things it simply cannot see. It cannot detect plate tectonics on a distant world. It cannot measure magnetic fields. It cannot see moons smaller than a certain size. And these three factors may be the most critical ingredients for life that we have not yet tested. Plate tectonics recycles carbon, regulates the climate, drives the geologic processes that keep the planet stable over eons. A magnetic field protects the atmosphere from being stripped away by stellar winds. A large moon might stabilize the axial tilt, preventing climate catastrophes. Webb gives us nothing on these. It is a breathtaking instrument, but it is not omniscient. It can only show us what is there. It cannot show us what is missing. So we are left standing at the edge of a new frontier, with more questions than answers. If planets that should not exist are everywhere, if our textbooks are wrong, if our models are broken, if the very definition of habitability is crumbling, then what else have we been wrong about? Webb did not just discover new planets. It revealed the limits of human imagination about what is possible. It shattered the walls we built around our understanding. And in doing so, it gave us the greatest gift a scientist can receive: the humility to admit that we are just beginners. The universe is stranger, richer, and more alive than we ever dreamed. And we are only now learning how to see it. And so we return to where we began. We started this documentary with a set of rules that felt ironclad, carved into stone by decades of astronomy textbooks. We believed we understood the cosmic recipe. You need just the right amount of dust and gas, a stable orbit, a star that behaves itself, a planet that forms fast enough but not too fast, and an atmosphere that clings on for billions of years. Those were the pillars. And then James Webb looked at the heavens and said, "No. Not a single planet we have found follows the script we wrote. Every one of them is a contradiction. Every one is something that should not exist according to our models. And that is exactly the point. The exoplanets that should not exist are not freaks of nature. They are the new normal. They are the rule. And we are the ones who must rewrite the textbooks. Let's sit with what this really means. There are 3 implications here that shake the foundations of how we think about the universe, and each one is more humbling than the last. First, planet formation is not the slow, stately process we imagined. It is faster, more chaotic, more violent, and far more creative than any simulation dared to predict. These giant planets swirling around tiny red dwarf stars, these gas giants forming in a cosmic blink of an eye near the hearts of collapsing nebulae, tell us that gravity works on a timescale we still do not fully grasp. The early universe was not a quiet nursery. It was a fireworks factory, and Webb is giving us the footage. Second, atmospheres. Oh, the atmospheres. We assumed that planets without magnetic fields would lose their air like a balloon with a pinhole. We assumed worlds too close to their stars would be roasted bare. We assumed only a narrow band of chemical compositions was possible. And Webb blew all of that out of the airlock. It found atmospheres thick with water vapour on worlds where there should be nothing but rock. It found hazes of sulfur compounds and carbon dioxide in proportions that defy every equilibrium model. It found methane on worlds that should be chemically inert. The resilience of planetary atmospheres is staggering. It means the conditions for life, for liquid water, for stable chemistry are far more common than we ever dared to hope. And the third implication is the one that keeps astronomers up at night, staring at their screens and whispering to themselves. Biosignatures, the chemical fingerprints of life itself. We used to think detecting them was a dream for our children. A decade ago it seemed like science fiction. Now, with Webb's data from K218b, from TRAPPIST-1e, from the rogue planets drifting alone in the Orion Nebula, we are not just dreaming, we are reading the ingredients. Dimethyl sulfide, carbon dioxide with a missing isotope signature, methane and oxygen in ratios that cannot be explained by geology alone. The signs are there, teased in the spectral data, hidden in the starlight that passes through these alien skies. We are within striking distance. The question has shifted from if we will find evidence of life to how will we recognize it when it is staring us in the face. And that brings us to the question that hangs over everything we have discussed. The Fermi paradox. You know the line. Where is everybody? It has haunted us for generations. If the universe is so vast, so ancient, so full of planets, why is the sky silent? But now we must ask a different question. What were we missing? What if the answer is not that they are hiding, not that they are rare, not that they have all died off, but that we were simply blind? We built our telescopes, our models, our assumptions, on a sample size of one Earth, one solar system, and we assumed that was the template. Webb is showing us the template was wrong, that life could look so different, so strange, so chemically unexpected that we simply could not see it. The burden of proof has shifted. It is no longer the duty of the universe to convince us we are not alone. It is our duty to look more carefully, to question our own biases, to accept that we might have been staring at the door all along and never noticed it was open. This is space. This is the new frontier. If you want to see where Webb goes next, what it finds in the smoggy skies of K2-18b, in the rocky twilight of TRAPPIST-1e, in the cold darkness of those rogue worlds drifting through the Orion Nebula, then subscribe to this channel. The documentary is not over. Every new data release rewrites the story. Every new image changes the map. Stay with us. The universe has been hiding its secrets for 13.8 billion years. Webb is finally teaching us how to read them.